In the second part of Lesson 2.5, where we're continuing to talk about compound inequalities, we're going to focus our attention on compound inequalities that have special case solutions or sort of unusual solutions. So when we talked about compound inequalities yesterday, or the previous lesson, we realized that most of the time, when we have an and statement, our solution is going to be the overlapping area between two boundaries. And when it's an or statement, the solution is going to be the region or the solution set of values that are shading away from each other. And most of the times, that is what happens. And in real life situations, most of the time, that's kind of the logical setup. But there are instances where our compound inequality has solutions that maybe both shade in the same direction. Okay, maybe they both go toward the left or toward the right. Or maybe it's an and statement, but the solution ended up looking like this. Or it's an or statement, and the solution ended up looking like that. So this really, what it requires, honestly, is just some sort of more in-depth thinking about what my solution really means. It's not necessarily going to be a difference in how you solve it. That part of it in itself is going to be exactly what we've been doing and what we talked about with just single inequalities and what steps it requires to solve those, and then how to deal with and or statements like we did in this last lesson. So really the added level of challenge in this lesson today is once we have this solution and once we take a look at how it graphs, being able to make a logical, reasonable conclusion of what is the true solution in that problem. Okay, and that really is going to take more than just some basic computation. It's going to take some deeper thinking. So there's not just a cookie cutter, one size fits all, but you really need to think about what your solution really means. So let's get started. One example is already done for you to kind of give you the idea here. This is an and statement. They want you to solve the compound inequality, graph the solution, then state the solution in interval notation. So we're taking it to that next level and practicing that interval notation again. So you have this and statement, but they're separate, different equations. So they proceed as we've talked about. Basically, they solve it each side individually. Here, they start off with the inequality. It looks like they subtracted x on both sides, got rid of it on the right. 2x minus x is 1x. So now we have a solution that says all the x's that are less than negative 1. So that by itself looks like this inequality right here. Everything that is less than negative 1. Okay. On the other side, you had this guy. So we could either distribute the 2 or we could divide it. Looks like they divided that 2 out of there. That leaves you with 5 here and just the x minus 4. And then they added the 5 and then they flipped things around. Well, for this and statement, the other solution is everything that is less than or equal to 9. That's the top graph. Well, in an and statement, I'm still only interested on where they overlap. So even though both of these are shading to the left, okay, both of these are shading less than, I still, if it is an and statement, I'm still interested, well, where are these both true? Like I have these numbers like 10. That is true for neither one. Definitely not part of the solution set. Those are not true for either of these. And then I've got some values right in here that are true for the top one. These values are less than or equal to 9, but they're not true for the second one. And in a statement that is an and statement, I'm not interested in these points either. I am only interested in where they are true for both. So I have to come all the way over here to the open circle and the less than, and it's really here where things really overlap, right in here, okay? It's that region that is true for both, okay? And so that ultimately is where our solution lies. So all of the x's that are less than negative 1 are true for this, and they're also true for that, because if it's less than negative 1, it's definitely going to be less than or equal to positive 9. Okay, so if it's less than negative 1, it's definitely less than 9, right? So anything that meets this criteria automatically meets that one. Okay, so you see how this is different. We're still looking for that overlap, but our only answer is where they're both true, which is really this more restrictive version, right? So that ends up being the solution set for the entire compound inequality, because it's the only region that makes them both true, is everything less than -1. So that's a solution for the entire thing, and then we can write that. So that's the big thing here. Let me just emphasize that. The graphs only overlap at that place right there at x is -1. And so when we write that as a interval notation, that's going from -infinity up to -1, not including either. So that looks like this. Okay. Okay, so let's take a look at number 11. This starts on 11 because it was kind of a continuation of the previous set of notes. But if we look at number 11, same thing. Our computation part isn't going to be any different. Okay. So on this one, we'll start off. Here's our or statement. Sometimes it makes sense to kind of identify that so you can figure out, okay, this is one inequality, that's the other. So let's go ahead and get started here. I always start with simplifying. I'll review here. There's no grouping symbols that I need to distribute into or get rid of. So I'll then move on to the next concept here, which is like terms. Okay, I do have a couple of like terms right in here on the same side, so I can combine those. 9x and -4x can be written more simply as just 5x. So 9x minus 4x is 5x. I still have the -5 constant. That is greater than or equal to, and then I have 3x plus 5 on the other side. There are no like terms there, so we're okay. That's step 1 out of the way. Step 2 is to gather these variables. Since I have variables on both sides, I want to pick one of those and do the opposite sign so that it cancels, and I'm left with x's in only one location. So that takes care of that step there. Now I only have 2 x's left on the left because I decided to remove 3 x's from the right and 3 x's from the left, and now this is all I have left. And x's are in one location only. And then last but not least is step 3, which is actually isolating that variable by undoing the operations, doing the inverse of those operations. So we'll start with moving the 5. That's usually where we begin. 2x is now greater than or equal to 5 plus 5 is 10. And then in round 2 of solving, we get rid of the 2 by doing the opposite of multiplication, which is to divide. So we get that x here is greater than or equal to 5. Okay? All right, now let's solve the other side. So in this other side, I'm going to distribute this 2 because there is a grouping symbol. Step 1 is simplifying. And I'm going to go ahead and just bring this or statement all the way down. So on this one, 2 times 3, that's 6x. 2 times 1, that is a positive 2. I have 5x on the other side. Still need to gather my x's. I like to keep my x's positive personally, so I'm actually going to move these. That might make you feel a little uncomfortable because you're like, wait a minute, that's all that you have over there. What will you write if you take it all away? Well, we'll write a 0 because there'll be nothing there, and that's okay. I'd rather have a 0 here and have x's on the left and positive. That's a win-win for me. Worth it. But you could have done -6, -6. That's okay too. But yeah, it's okay to do that. I just moved the x's. I have nothing left here. I say that. We have a name for that nothing. It's 0. There it is. Okay. So once I have 6x minus 5x is x, now I can go to solving. All I have to do is move the 2. So I get that x is greater than or equal to 0 minus 2 is -2. Okay. Okay, so let's see what happens when we graph this. Okay, let me go ahead and pinpoint some values here. Let's say we've got a little bit more on that side. So I'm going to put 0 here, -1, -2, -3, 1, 2, 3, 4. There's 5, 6, 7. Okay, so this is an or statement. As long as it's true for at least one, we are good. I don't need them to overlap. Okay, anywhere where there's shading is going to be a solution here. So when we go to graph this, I want you to look at what happens. This inequality is all the x's that are greater than or equal to 5. So if I come here and I say, okay, everything greater than or equal to 5 is right here at 5, filled in, and greater than, which means to the right. Okay, and then, or all the x's that are greater than or equal to negative 2. Well, oh, wait a minute. That goes in the same direction, right? So, or anything that is greater than or equal to 2. Well, they're both greater than symbols. They're both going to the right. And if this had been an and statement, I would be limited to the shorter line, if you will, to this more limited section where they overlap. But this is an or statement, so as long as it's true for at least one, we're okay, which means our solution set really starts all the way back here at negative 2. As soon as we start at negative 2, we have solutions for at least one, and actually eventually both, but who cares? We don't even worry about that because I have always, everything from negative 2 and greater has a solution to at least one of these inequalities. Well, that means that our final solution here is just all the x's that are greater than or equal to negative 2. That is a solution to the entire compound because this meets the criteria for the entire or statement. Okay, so you can think of it that way. When they're shading in the same direction, if it's an and statement, then it's going to be essentially the shorter one where they overlap and both are true. If it's an or statement, it's going to be the one that has more solutions in it, the longer line, because as soon as it starts being an answer to at least one, we're already started. That's already part of our solution set. So same thing here. If this was an and statement, so it was just this short little section where they overlapped. But if this had been an or, then it would have, anything starting at 9 and below would have worked, because as soon as we hit here, we start getting points that are a solution in at least one, eventually both. But starting here, we start to get points that are at least solutions in one of them, and that is good enough for an or statement, okay? So when they're shaded in the same direction, the shorter overlapping part is a solution if it's an and then the longer answer that's, an answer to at least one is the answer if it's an or, okay? So you got to think about your solution and what it actually means or represents there. The solving steps, they're the same. There's nothing new there. At this point, we've done that so much. I really hope that is feeling really comfortable. So it's really about analyzing your solution and what does it mean to be an answer in this or that. Well, these guys, they don't have to overlap. So starting at negative 2 and on toward the greater side, it all works. Okay. All right, let's try number 12. Same thing. Here's our or statement. Identify that guy there because it tells us what kind of compound inequality it's going to be, and then also kind of separates this long string of stuff. So let's simplify here on the left side. 5x plus 3, nothing we can do there. But here I can definitely distribute that 4, and I'll get 4 times x is 4x, and 4 times 1 is 4. Then, now that both sides are simplified, I'll go to step 2, which is gather the variables. So I'll pick one of those and do the inverse. I'll remove 4x's from this side so they're not there anymore. But I have to also remove 4x's from the other side. 5x minus 4x, that leaves me 1x. That leaves me 1x left after that with that positive 3. And that side is less than 4. And then last but not least, step 3, we start to actually isolate our variable and solve it. The opposite of adding 3 is to do a negative 3. So I get x is less than 1. Okay, so that's one of our inequality solutions. Or let's find out what the other set of solutions could possibly be. So we're looking at let's see, 2x minus 5, that's already simplified. But over here, I want you to notice we do have a couple like terms. So we can combine this 6x and the negative 3x. They're on the same side. So 6x's minus 3x's leaves us with just 3x's. On this side, we've got 2x minus 5. Okay, step 2, gather your variables, right? So I've got a couple options. I could move it this way. It's going to give me a negative, okay? Or I can move it this way, but then the x's will be in the wrong side. pick your poison. They both work. I'm going to keep things positive. I like to keep things positive. I'm a positive kind of person. There you go. So I'm going to take 2 x's away, and that gets rid of them on the left side. But on this side, I still have 1 left over. I had 3 x's. I take 2 away. I still have an x. Okay, so I got x minus 11. And then in the next step, I can actually isolate this by doing plus 11 on both sides, or a positive 11. This gives me a 6 greater than or equal to x. I don't like the way that reads. It is hard to interpret and understand. So when I write my final answer, I will rotate that. So x can be either anything less than 1 or anything less than or equal to 6. Okay, that's our solution here for the or statement separate inequalities. But when I realize this is a special case, that solution might actually be a little simpler than that. So again, when we graph this, and these are both positive, so I'm going to focus here on the positive side. One solution is all the x's that are less than 1, so open circle and shading to the left, okay? Or also anything that is less than or equal to 6. Well, that's also going to the left. That's also a less than. And since this is an or statement, right, as long as it's true for at least 1, then it's going to be a solution to the whole compound. So really our final answer is where at least one of them is true. Well, that starts all the way back here, right? It's the longer line. Everything from 6, including 6 and less, is definitely has a solution in at least one, if not both, but definitely in at least one of these. And so our final answer here is all the x's less than or equal to 6. Okay, so that kind of region, maybe we'll use a highlighter here. So this one ends up being the answer for the whole thing. Okay, for the whole or statement. That everything from there to there is a solution in at least one. Okay, let's try number 13. This one's actually a pretty interesting problem. I want y'all to check this out. This is an and statement, so that's important to note. I'm only interested in what makes both of these true. It's not good enough to be true in one and not the other, like a minute ago. This one is only the overlap, right? Only the overlap. Keep that in mind. Okay, so let's do the left side. This is a game changer, right? We already know there's a game changer with that division bar. It changes the order of things. It makes me, instead of having to get rid of the addition and subtraction, it makes me have to get rid of that denominator first. So I've got to multiply by 3 on both sides here, so that this no longer looks like that messy fraction that it looks like. It's just 7x minus 5, and it's greater than or equal to, and then 3 times 3 is 9. Okay, and now I can solve for x here. Now I can start by just eliminating and using those inverse operations. So 7x is greater than or equal to, and I get a 14. Looky there. They didn't make this so bad for us. This divides nicely. It's divided by 7 on both sides. We get all the x's greater than or equal to 2. There it is. Okay. Now let's go ahead and solve the other one. Nothing to simplify, no like terms, no grouping symbols, but I do have x's on both sides. So I've been moving things to the right to keep things positive. Let's practice for just a moment what would happen if we didn't. Let's move the 4x this way. Okay, I'll gather my x's to the left this time. I'll do negative 4x, it cancels them on the right. On this side, positive 3 with a negative 4 is just a negative x, or a negative 1x if that helps. Plus 1. Symbol still greater than or equal to, at least for now. And over here, all I have left is that negative 1. Okay. Next thing is to solve for that x. So let's get rid of that addition of the 1. Do the negative 1 on both sides. That'll get rid of that. So now I'm down to a negative 1x, or a negative x is greater than or equal to, and this side, negative 1, that's negative 2. Well, we still have to fix this. We're not done. So we got to get rid of this negative. We are going to divide by a negative on both sides to get rid of that sign. But when we divide by a negative on both sides or multiply, we flip that sign. Okay, so this is the other inequality. So I want only the solutions that make this true and that true, because this is an and statement. Okay, so they have to overlap for it to be a solution. Well, let's graph these and see where they overlap. Okay, if we make our graph, let's see, we'll do -2, -1, 0, 1, 2. That should be enough. So for this one, the stuff that makes this guy true is any x that is greater than or equal to 2. So for that, greater than or equal to 2, I will make a closed circle on 2, and it would be everything greater than. That would be that inequality by itself. Let's see what makes this guy true. This one's all the x's that are less than or equal to 2. Okay, so less than or equal to, that's an all closed circle, and everything less than. Okay, interesting. Okay, and statement. This is super important. I only want where they overlap. Well, there's only one place they overlap, and that is right here at 2. That's it. Everything else is a solution to one, but not the other. And on this one, it's a solution to the other, but not the first one. And so right in here at 2 is the only place where we have an overlap. So what an interesting solution to a compound inequality. The only solution that makes this true is when x is exactly 2. That's it. Anything outside of that wouldn't be true for both. Okay? And so that is our solution. Just where x is equal to 2. That's it. Boom, just that point. That's the only solution. Even though it's a compound inequality. Now, just for fun, let's think for a second if this had been an or statement. If this had been an or statement, as long as it's true for one or the other, then it would work. Well, if this one is 2 and everything less than 2, and the other one is 2 and everything above, if for an or statement, this would have been all real numbers. This would have been the entire number line. So just for fun, just understand that. If this had been an or, this would be all real numbers. Every single number in the universe is either greater than or equal to 2 or less than or equal to 2, right? It's either greater than 2 or less than 2 or 2. So yeah, that if it were an or statement, every number would work, all real numbers. But because it's an and statement, this is exactly the only number that would ever be true for that and statement. So there you go. So again, the steps are the same. The solving part is not hard. It's the analysis, the interpretation. What does this mean? And really, how does that affect what our real final answer is? That's where the edit challenge lies today, okay? All right, let's try number 14. So in number 14, let's see what happens here. This is an and statement. Okay, let's do what we've been doing. Just kind of solve each side and then interpret the solutions. So here, everything is solved. I'm going to go a little bit faster. This is practice. We've done it for so long. I think I can hopefully walk it a little faster and you can follow along. So I'm gathering my x's to one side. That's going to leave me with -18 is less than, and on this side, I'm going to just get x and a -23. And then to get x alone, I am going to add 23 on both sides. So that leaves me with 5 is less than x, but we know we don't like to read it that way. So we switch it around. We say all the x's greater than 5. Okay? Okay, so there's one solution. And then again, just a reminder, this is an and statement. Let's solve the other side. Well, the other side's pretty simple. Thank goodness. X is almost by itself. They're just subtracting the 16. So we're going to do the opposite, which is add that 16, or a positive 16. And that takes us to x being less than. And that comes out to a -6. Okay, so this is the initial solution. And I'm going to go ahead and set up our graph here. We have a little bit in each side. Geez, okay. Maybe I need to go by 2s on this one. I might have to go by 2s. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay. So one solution here is all the x's greater than 5. So if I graph that, that would be right in here, greater than 5. Would look something like that. The other solution is all the x's less than -6. So that graphs this way. okay? But this is an and statement. So I ended up with inequalities that were shading away from each other, and yet it's an and statement, and I'm only allowed to select the final region where they overlap. Well, do these overlap? No. There is nothing ever that's going to be both less than -6 and also greater than 5. There is no number that's ever going to be that incredible. So this has no solution. Okay, so yes, we have these inequalities, but there is no solutions that satisfy or meet the requirements of this compound inequality. Okay, there just isn't. That's not going to happen. So be careful. Don't box this, right? In a situation like this, I'm going to be looking for that final important analysis of what the true real answer is here. Okay, all right, I'm speeding it up even more. I keep saying that, right? All right. And statement, always make a note of what kind of statement that's going to help you analyze your solution. It's an and statement right there. I'm going to solve here, isolate my y. And then I have that negative, so I'll have to divide by a negative on both sides. And that, of course, flips our sign. So I get that y is greater than or equal to a -5. On the other side, I'll subtract 2. And I will get that y is greater than 7. And this is an and statement. So I want everything that is greater than or equal to -5 and also greater than 7. So when we graph this, I am probably going to, once again, let's see, what do I want to do? I want to go by, so if I make this, I need to get down to -5, so we'll put 0 here, and then -1. Nope, see, that's still not going to fit. Okay, we're going to go by 2's here. Okay, so it'll have to look like that. And then 2, 4, 6, 8, 10. Okay, that should give us enough space. All right, so when we graph each one, these are the y's that are greater than or equal. That's right here in the middle, greater than or equal. So those would be those solutions. And then the other inequality is any y values that are greater than 7. So open circle and also greater than. And it's an and statement. Ding, 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 ding. So I can only acknowledge and finalize the region where they overlap. Or where do they overlap? They start overlapping here, the shorter section of this, right? Here they're solutions, but only to one. If it's an and statement, I need it to be a solution to both, right? So my final answer here is the region where x's are greater than 7. And it's this part of the graph. So anything greater than 7 is greater than 7, and it's also greater than or equal to -5. It meets both criteria, okay? So I think y'all are getting the hang of this. I'm going to finish out these last two just so we have a couple more examples here. Let's start with this one here. Already simplified, already variables on the same side. I'm going to just isolate r. That gives me -108. And then I'll divide both sides by a -12. And I get that r is, less than or equal to 9. Because I divided by a negative on both sides, I have to flip that sign. And I get that r is less than or equal to 9. And this is an or statement. Okay, on the other side, I will add 4. I'll get that 2r is less than, and this will come out to a -8. And then in the next step, I will divide by 2, and it's a +2, so I don't have to worry about flipping anything. I'm not dividing by a negative number. I'm dividing by a +2, so this stays less than, and it's a -4. So it's an or statement. As long as it's true for one or the other, we are okay. So let's go ahead and graph and see where that final region is. This is going to be a wide one too. Okay, we're going to put, let's see, let's hope this works. We'll put -4 here. 0, 2, 4, 6, 8, 10. Okay, it worked. So one solution is all the R values that are less than or equal to 9. So 9 would be right here, less than or equal to, would look like that. And then the other solution is all the R's that are less than -4. So open circle on the -4 and less than. But it's an or statement this time. So it's an or statement. So as long as it's true for at least one. So over here, nope, doesn't work. Boom. As soon as I hit 9, I have values that are a solution to at least one of these. So everything, that longer line, right? Anything from 9 and below will work in the or statement because it'll have solutions to at least one of these. So our final solution here is there are values that are less than or equal to 9. Okay, and then our last one. This one is an or statement. Let's see what that looks like. Okay, we have on one side, x is almost by itself. All we have to do is do a positive 6 on both sides, and we'll get that x is less than or equal to 9. And then, or on the other side, we'll take away the 5. We'll get 2x is greater than, this comes out to 2. We'll divide by 2, and we'll get that x is greater than 1. So here's my solution, my work that has the evidence. So as long as x is either less than or equal to 9 or greater than 1, we are okay. So let's find out where that region lies, if at all. So when we graph it, these are both positive. So will it fit? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Woo! Okay, we made it. I want any values that are less than or equal to 9. So here's my first boundary number, less than or equal to 9. So including 9 and anything below, that would be fine. Or anything greater than 1. Well, here's 1. Anything greater than 1 points in this direction. Well, it's an or statement. That's the part that's super important here, right? It's an or statement. So they don't have to. If they overlap, well, good for them, happy for them. But they don't have to overlap. As long as it's true for one or the other, it's a solution to the compound inequality. Well, guess what? Any number is either going to be less than or equal to 9, because this goes, on forever, or greater than 1, that goes on forever, right? Everywhere I put down, like my pen, it is a solution to one or the other. Guys, this is the entire number line. This is all real numbers. So this solution here is all real numbers. Any real number you pick, you can plug in here and it'll be true either for this one or for that one. So any real number will work, okay? So again, last thing, all of this part was review, right? Everything we did here was completely familiar and practice and review. There was nothing different about how we solved them. What was very different is how we interpreted those solutions, right? Really stopping to think about what that means and whether we want, the shorter where they overlap, if it's an and statement or any point that works, for an or statement. So that's where you have to be careful, think it through, analyze your answer carefully, and make sure it's a complete and honest and correct answer.